Yeah, hello students, greetings of the day. This is your Eknath sir from VIP classes.
What we
Today we'll
discussed in
talk about
gravitation, right? What
gravitation. Okay?
subtopics are there in gravitation, right? Yes? A topic is the which topic? This basic question I'm asking. ఎక్కడ ఉంది ఫస్ట్ ఇయర్ ఉందో in first year we have. So what we have studied in gravitation, please? What are the main headings which you have discussed? Yeah? Planetary motion. Okay. That is Kepler's laws. Yes or no? You can just broadly recall what you have studied in Kepler's laws and in case of gravitation, Kepler's law. Okay, satellites you have seen, isn't it? And then we have gone for what? Newton's law of gravitation. Yes or no? Yeah. Newton's law of gravitation, isn't it? Yes or no? And principle of superposition we just studied in this one. So when system of more than one particle, two particles, you can find out 2 point masses, we can find Newton's law of gravitation. By using principle of superposition, we can find the force of interaction between what, ray? Different kind of molecules or atom here. Point masses, what I mean to say is 3 particle, 4 particle, 5 particle, like that, okay? By using principle of superposition. After this, what you have studied in this one? After gravitation, Newton's law of gravitation, finding the force between different point masses by using principle of superposition. And how do you apply this concept of Newton's law of gravitation for extended bodies, okay, or larger size bodies? That also we have seen. And then will discuss about what is potential energy. Okay, then we go for potential energy and potential. Okay, then we consider about what is potential, isn't it? And then we will be studying about potential and potential energy for two particle system, you can say, or potential energy, potential because of a point mass, potential because spherical shell, symmetrical bodies generally we talk here, okay, those expressions we have seen. And then we will be seeing for planets and satellites, which one question we will be studying about. Before this potential energy, Newton's law of gravitation. So here we also study about field, gravitational field and its intensity. And what? Gravitational GF, gravitational field intensity. Okay, the gravitational field intensity itself we call as acceleration due to gravity. Yes or no? So those second point extension I'm writing here, right? The variation value of G we studied. Variation in value of G, variation value of acceleration to gravity, with height how it changes, with depth how it changes, and all those parameters, isn't it? And last part we study about satellites and orbital motion, geostationary satellites and all, and what are the expressions for orbital velocity. Okay, next escape velocity, orbital velocity, comma escape velocity. So these are the things which you generally measure part of the gravitation, isn't it? Yes or no? Yeah. Now, if you consider, so the gravitation part itself, the world is fascinating, the universe is fascinating. So how stars are, okay, in optics part you also how stars are twinkling, okay, how sunrise, sunset, rainbow formation, mirage formation, and we're using optical instruments for seeing the celestial objects like planets, okay, satellites, moons, isn't it? So when you observe them, and we got wonder how actually all these objects are. See, people in the beginning they thought that, yeah, sun is moving from one part of the sky to another part of the sky, so we thought that sun may be revolving around the earth. Planet is what you can call, stars may be revolving around the earth, like this different imaginations people use it to think. The first scientist, okay, who actually thought in that direction is, his name is Ptolemy. Okay, so Ptolemy scientist, and he proposed a theory regarding this particular motion and all, that is called geocentric theory. Okay, geocentric theory. So what this theory says, no, so for entire universe, earth is the center of whole universe, right? Earth is the what? Earth is center of what? Whole universe. Earth is center of whole universe, and all planets, okay, including sun. Earth, okay, in our solar system, sun is okay. We are not considering sir. Just now, current status of understanding the universe is now in our Milky Way galaxy. Sun is there around the sun. Planets are revolving. So before thought, before this one actually, okay. In the beginning, people thought like this. This scientist named Ptolemy, he proposed a theory, Ptolemaic theory or geocentric theory. Earth is the center of whole universe, and all planets, including what, including sun, revolve around the Earth. Revolve around earth in what path re? EARTH. Okay, around the earth in circular orbits, circular path, you can circular orbit. Okay, this was the proposed theory, and for hundreds years, nearly hundreds of years, this theory was accepted. No one commented. Yeah, everyone accepted like that. After this scientist, next one more scientist came. His name is, can anyone tell? Yes, Copernicus, and he proposed a theory known as helio. Geo means earth. Earth as center of the universe is called geocentric. Here Copernicus proposed helio. In Greek language, helio means sun. Okay, heliocentric theory. This scientist came, okay, and he proposed no, earth is not the center of whole universe. Sun is the center of whole universe. All the planets, including earth, they are revolving around the sun. Okay, in what orbits? In circular orbits, he mentioned. This theory is known as Copernicus theory or heliocentric theory. Okay, so after this was investigations are going on, this theory was accepted few more years, and then so one more scientist name came here, Tycho Brahe. Okay, so Tycho Brahe, this scientist spent a lot of time on the celestial motion, okay, how the celestial objects are moving, and he prepared, and at different times he observed the position of stars, moon, earth, sun, and all those things, and he come up with some conclusion or thesis or document. Okay, and under him one particular research scholar was working. Okay, that research scholar name is here Kepler. Okay, by observing his master's doctrine, okay, doctrine or documentation or thesis or theory, so he proposed few laws regarding planetary motion. Okay, so laws of, okay, Kepler's laws of planetary motion, you can call them. Okay, Kepler, okay, laws he proposed, and these three laws are famous, and they are actually, he included some mathematical part also. They're not simply assumptions of his master Tycho Brahe. He has not taken, he has used some mathematical tool for understanding. Okay, and he could able to explain successfully so how the planetary motion was going on by mathematical analysis, and that was come to true, and nowadays we're accepting that almost, okay, same. And the first law he mentioned about, now whatever the people they said in the beginning, are you hearing all of you? Geocentric, you can say, heliocentric, you can say, and all those, he said that yes, he accepted some part of heliocentric theory. Yes, sun is the center, okay, but not for the entire whole cosmic manifestation, only for our Milky Way galaxy center. Sun may be the center, and around the sun all the planets are revolving, of course, but they are not in circular orbit. He mentioned elliptical orbit, and he gave the statement, okay, the path of the planet around the sun. Okay, nowadays whatever we're accepting, no, that is what, that gives in terms of a law known as law of orbit. Okay, and what is law of orbit here, what it tells? So the path of the planet is what? Elliptical. The path of the planet is what? Elliptical. Fine, everyone. The path of the planet is elliptical around the sun. This is called law of orbit. And second law, what he proposed, no? So you know everyone what is ellipse in geometry. Also you studied in mathematics what is ellipse, equation of ellipse, standard equation of ellipse, x square by a square plus y square by b square minus 2xy by ab into cos phi is equal to 0. Our standard equation x square by a square plus y square by b square is equal to 1. If a is equal to b, the ellipse becomes circle. All those things we studied, isn't it? In mathematics now you are full-fledged. Why? Because the entire syllabus over, we have the knowledge of first year and second year. This is a revision schedule. So therefore, you know, ellipse actually, if I have a point and a line, the locus of set of points, okay, point and line, such that the ratio, what is the definition of ellipse? Can anyone tell me? I would like to know from you. My definition is different. Please, can you mathematics definition, can you tell me? I studied in long back, 20 years back. I didn't remember anything. All this ellipse and the conic section and all. Can you please recall the definition of ellipse? Line and point equation. Omkar? Hello. Can anyone tell the ratio? Hello, definition of ellipse chapter evarana? Yeah, or else you see this will be two fixed points will be there. Okay. Now, if I have this wire kind of thing, right? Okay. So if I take any particular point, the ratio from these two, okay, The ratio of these two is always constant. So you can take from here to here, here to here. Okay. So now if I take this ratio of distance from these two fixed points, if a point is moving around these two fixed points, or you can imagine two lines are passing through these fixed points. According to physics, we tell like this. I don't know about mathematics. So now here, if I take this distance to this distance, always constant here. Okay. So the locus of all the points. Okay. So locus of all the points which are equidistant from these two fixed point. Okay, such that the ratio. So this particular length plus this particular length, if you consider, no, constant, or else simply take a wire like this, ray. Okay, and what you do, fix these two points ends of the wire, and you just stretch this wire here, so it will take this kind of shape. Next, stretch to this side, so then this distance take this kind of shape. So this kind of for locus of all this point, if you go on join, it forms a elongated circular shape that we call as here ellipse. Okay, in mathematics way of defining is different. Okay, no one is telling, no. So we actually in physics consider this by assuming that the curve and all. Okay, so elliptical path. So here we on the elliptical path, so we consider here this is major axis, this is minor axis. So major axis length we call as 2a, minor axis length we call as 2b. Okay, so semi major means half length. This is a and this is b. Okay, so what happens? So there are two fixed points on this major axis we call foci, that is f1 and f2 are called what, foci. Here sun either may be over here or sun may be over here, doesn't matter, and the planet is revolving around the sun along this different positions. Okay, around the sun. Sun may be at any one of the focus. So all the planets, not only this, remaining others. Say for this is what one another planet, another planet. So another planet like this. Sun being at one of the foci of this elliptical path, remaining planets are revolving around elliptical path. This path of the planet is elliptical. Second one comes out to be, now when I consider, say for example, on this major axis we have 2 points, fixed points, which we call foci here. This is first focus I can call, this is second focus I can call. Planet is revolving around the sun. Say for example, sun is over here, this distance. If you see, the distance of the sun is go on varying over here. Okay, so go on varying. So we take average distance, we take actually. Okay, so fine. Now when the planet is moving around the sun, say for example January month 31, February 28, again say March again 31, no. So fine, I am observing in January month, and say March month also I am observing 31 days I am observing. So planet is in during this 31 days from here to here has gone. If I measure this area traced by this radius vector to different positions of this planet in one particular duration of time delta t, if I call it as a1, in same amount of time delta t, if I take again the area vector swept by this line joining the planet to the sun. Okay, area vector, so this is e2. So he has found that, so this area swept by a planet around the sun in equal intervals of time is same, in same amount of time. So displacement by time is called velocity here, area by time is called areal velocity. So this particular law, okay, he defined and he calculated, right? This is called law of areas. So we'll frame the definition now. The line joining planet to the sun, the line joining planet to the sun sweeps out equal areas in equal intervals of time. Okay, this is known as law of area. So a1 by a2. So if, for example, this is sun here. So planet was over here. After some time, planet has gone over here. So arc it has traced it. This is the area. For small amount of time delta t, I can take approximately average radius r. This angle is here theta. Area of sector, you know very well formula, half r square theta. So rate at which this radius vector is moving is the rate at which this angle also changing. So angular displacement by time we call angular velocity here. So if I aerial velocity, if I want a by t, if I do here, that becomes half r square. If I take this small angle delta t by delta theta by delta t, if I divide this t here, okay, listen. So if I divide with time, so delta theta by delta t is called angular velocity omega. So half r square omega. Therefore, you can find out that aerial velocity is given by simply formula half r square omega, where omega is angular speed of the planet around the sun. Okay. Now, so if you multiply and divide with m over here, so you can find out, Ray, all of you keep in mind, 1 by 2 m okay, r square omega. So if linear speed of the planets, okay, if v, so if this average radius vector, if I take r, I can relate it as v is equal to r omega. So I can arrange this statement like this. So m into, okay, r omega into r. So this is v. This is MVR. MVR is angular momentum. So angular momentum by time. So you can express here aerial vector or aerial velocity, area by time. This aerial velocity is coming as in terms of angular term, angular parameter and mass of the planet. So just I would like to keep in other words, look at the board carefully. So this is the 1 minute stuck, right? Can you see the board? Yeah. Now this is the elliptical path. Major axis, minor axis, sun is over here. So this is planet ankundam. About sun, if I consider, okay, see as well as we have known that how the planets are able to means the gravitational force of attraction acting. Why? Because see, we are in revision part. I am not teaching newly this topic. So you know that why the planet is revolving around means the gravitational force making it to revolve around the sun. That means so on the planet gravitational force because of sun is acting like this. This is planet, this is sun, this is position vector of the planet r bar, and on the planet gravitational force acting like this. So if I consider as it is revolving here and going from p to p dash position, radius vector is rotating here. So if I consider torque of the gravitational force about sun, torque of the gravitational force about sun is r bar cross f bar, that is r f sine theta, where theta is angle between position vector and force vector. Position vector is like this, force vector is like this angle is 180, so opposite angle, so sine 180 is 0. So torque of this particular gravitational force about center of the sun on the planet is equal to 0. Whenever torque about sun of the planet is zero, so rate of change of angular momentum dl by dt is zero. When rate of change of angular momentum is zero, there is no change in angular momentum. There is no change in angular momentum means angular momentum is constant. This is what conservation of angular momentum. So approximately for small at different instance, if we consider a different instant, if we consider this is say for example sun, this is planet in a small amount of time, so it's shifting like this, no. So if I take this as average radius as r, if I take speed of the planet, if I take as v, okay, so angular momentum of this planet about this one is mv into r. Almost you can take very smaller theta, no. So you can take velocity is tangential, this is radial, almost this angle 90 తీసుకున్నా మీరు. Angular momentum simply you can write r bar cross p bar, you can write down r bar cross p bar is constant, you can write, or r into mv, r bar cross m into v bar is equal to constant రాసుకోవచ్చు మీరు, లేదా for approximately for smaller angular displacement simply mvr కూడా రాసుకోవచ్చు. Okay, doesn't matter here. So if we mention, if not means you should simply take r bar cross p bar. This is p bar momentum vector, this is r bar vector, r bar cross p bar nana. So if it is circular, if he says, no doubt at all, in circular direct, velocity will be perpendicular to radius, so angle 90, sine 90 is 1, so mvr raskochu. Okay, so if you consider overall, what is the conclusion here? Torque of this gravitational force of the sun on the planet about its center is becoming zero. Angular momentum of the revolving planet or the satellite around the sun or any other celestial object becoming equal to zero. Angular momentum constant is mvr constant. Of course, mass of the planet definitely constant, so you can write v into r is constant. So from this you can write down this r is inversely proportional to v. What the meaning of r? So this r, this is r, distance of the planet from the sun. When this value in case of elliptical path is go on changing, so when r is small, here v is larger. Why? Because v into r is constant. And when r is larger farther from the sun, okay, v value, okay, is slow. R into v is constant. So when r is large, v is slow. Therefore we can understand from this that, so when angular momentum of a planet around the sun, angular momentum of a planet around the sun is what? Constant. So when the planet is moving around the sun, okay, very important point there. So when the planet is moving and the planet is what? Moving around the sun, okay, its velocity changing. So when it is nearer, okay, when the planet is moving around the sun, you can write statement its angular momentum is constant. Why constant? Already I explained. Its angular momentum is constant. Due to this, okay, due to this, when the planet is closer, when the planet is closer, when the planet is closer, its speed is larger. Its speed is larger. And when the planet is farther, when the planet PLA, when the planet is farther, the planet is farther, its speed is lower. Speed is lower. Okay, therefore keep in mind. So whenever the planet Yeah, so here when the planet is farther, its speed is what? Lower. When the planet is closer, its speed is larger. This is based on what we are explaining here, conservation of angular momentum. Therefore, sometimes in the exams also will ask basic question it is. So why it is means due to conservation of angular momentum. Sometimes in the option they are asking when the planet is revolving around the sun, the angular momentum of the planet is constant. First statement. Second statement, when the closer, when it is closer, its speed is larger. When it is farther, its speed is what? Slower. This is value is giving r1, so velocity is v1. When it is at r2, its velocity is v2. Okay, so as r2 is more than r1, so definitely v2 is lesser than v1. This is explained based on what? Conservation of angular momentum. Is it okay, everyone? Therefore, this is how the story goes on, that planets are revolving around the sun elliptical orbit, and the path of the planet around the sun is elliptical. And second one last says that law of areas, the planet revolving around the sun sweeps out equal areas in equal intervals of time. So we can also say aerial velocity of the planet is constant. So aerial velocity is given by what formula? Half r square omega or 1 by 2m mr square omega, or simply this also so many times in the JEE mains asked aerial velocity questions adigaru, L by 2m. And we have seen that angular momentum is constant. So when angular momentum is constant, m is constant, L constant, definitely aerial velocity is constant. So indirectly you can say this is a kind of proof for Kepler's laws that the planet revolving around the sun sweeps out equal areas in equal intervals of time. Okay, this is what aerial velocity is constant, conservation of angular momentum. When the planet is closer, speed is larger. When the planet is farther, speed is smaller. I hope I am clear so far. Right, everyone? Intra. Are మాట్లాడండి bhai. Yeah. So this is what conservation of angular momentum of a planet around the sun. This is what law of areas. And next third law by proposed by Kepler is, can anyone tell what is Kepler's third law? మీరు చెప్పాలి రివిజన్ బై కొత్త పాఠం చెప్పట్లేదు నేను. Kepler's law of what? Time periods. Can anyone recall? చెప్పండి ఏంటి ఫార్ములా ఏంటి చెప్పండి. That's why we are correcting formula test. No one knows even formulas also.
Square of
Yeah.
time period is directly proportional to radius, cube of radius.
So the square of the time period of the planet around the sun is proportional to what? Cube of the average radius vector. Why we are taking average? See, when the planet is moving, around the sun in elliptical path, see this distance is go on changing, varying here, isn't it? Maximum again now decreasing, decrease, become minimum. Sometimes minimum and maximum antarra. When it is closer, this is minimum. Maximum is they should be diametrically opposite. Then what you can say here? This r1 plus r2 is equal to what? 2a. From some questions will be framed on this one. R1 plus R2 is equal to A. Okay, when the planet is closer to the sun and farther from the sun, so what is the separation between them? Nothing but equal to measure axis length. Okay, అర్థమవుతుందా గుర్తుంచుకోండి. సో ఈ క్లోజర్ ఫండ్ నౌ కెప్లర్స్ లా ఆఫ్ టైం what is say, no? So as the value of r is go on changing, so we go for average radius vector as r will say. So effective average radius vector we say, and sun is over here. If effective average vector if I take as r here, so you can show that it is revolving around with this one. Okay, planet is revolving around the sun with some effective average. How do you find average, sir? Nothing. R1, R2, R3, R4 any sort of this code, no average this code. Average radius vector is sum of all r1 plus r2 plus so on and rn unte n సార్లు తీసుకుంటే n తీసుకో. If you take 10 positions, if you take here 10 తీసుకో, కింద కూడా 10 తీసుకో. If you take 12 positions, 12 తీసుకో, 12 తీసుకో. That's average radius vector. Okay, so what Kepler's laws of planet? So definitely planet is revolving around the sun. It is taking some time, no? So time taken to revolve once is called time period. So the time period, and with this average radius vector he related. How we related? The square of the time period is proportional to cube of the average radius vector. This is called third law. This is called what here? Third law. And generally for satellite and earth system, like moon and earth system, effectively we take this average radius. Definitely moon is revolving around the earth in circular orbit. So there if you want to find time of revolution is t here. And here also you can say effective average radius is r. This is what? Sun This is planet revolving, t square proportional to r square. Approximately by making this r as constant, and when the planet is revolving here, if we calculate the time taken for one revolution, v is equal to formula A, d by t, isn't it? T is equal to d by v. For one revolution, how much time it takes? 2 pi r. So its velocity is here v. Following. And why it is revolving, actually what making it to revolve around the sun here? Gravitational force. So on the planet, gravitational force acting. So whenever gravitational force acting and the particle is moving along circular path, means what is required? Centripetal force is required. So who is providing centripetal force here? Gravitational force of attraction between them is providing what? Centripetal force. Now, so here if you consider the gravitational force of attraction, already formula all of you know, Newton formula. If I have a point masses here, m1, m2, suppression is r, according to Newton. Okay, he's already know Newton's story in mechanics we have studied. So while he's studying the acceleration of the moon, okay, towards center of the earth, suddenly apple fell down, story you know. So, and then he said that generalized statement that all the planets are being attracted by every other, isn't it? In the universe, every object attracts every other object with a force he mentioned. That force proportional to product of the masses inverse from square of the distance, and we got conclusion what? G m1 m2 by r square. Okay, in vector format. I will tell you once again this one. So just you are now take here. Now we are in Kepler's law. After I will go for Newton's law. So centripetal force how much now? So gravitational force providing. So G m1 m2 by r square. Say mass of the sun or Earth is capital M. Mass of the planet or satellite is small m. So G m1 m2 by this r square is equal to, see what I'm talking. This is Earth mass తీసుకుంటే the moon mass తీసుకోండి satellite. This is r. When this is revolving here, for one revolution time taken is t. Okay, so it doesn't matter. It anti-clockwise తీసుకోండి. So this is v here. So time taken is equal to 2 pi r. V is equal d by t is equal d by v. For one rotation means 2 pi r. Velocity is here v. So gravitational force of this particular earth on this particular mass is making it to move along what? Circular path. So circular path means centripetal force mv square by r. So mv square by r is r, radius of circular path. So here if you see, so you can call this distance as we are calling as r. This also get cancelled. With what velocities the satellite revolves around the earth, or effective average distance r తీసుకుంటే planet revolves around the sun is given by gm by r. This itself in future we'll call as the orbital velocity. Yes or no? Are you following everyone? This itself we call orbital velocity. Okay, now if I consider here this v square value, how much right? Gm by r. Now v value how much here from this one? Time taken will be 2 pi r by t. Substitute dintlo. So we have 4 pi square r square by t square is equal to gm by r. So from this we'll get t square value is equal to, very very important formula you have to remember, 4 pi square by gm into r cube. So where in case of planetary system, r is average radius. Okay, therefore you can say for a given planet z everywhere constant, mass of the planet is constant. So you can say t square proportional to r cube. It's the kind of proof for this Kepler's third law. By taking assuming actually average radius as, okay, radius of the path of the planet and sun here if you take no, so t square proportional to r cube. So this is called what? Times the square of the time period is proportional to cube of the average radius vector, which is known as Kepler's third law. Now you see, for a given planet mass m, for a given satellite mass small m, this time period is not depending on mass of the satellite man, depending on mass of the celestial object. This point number one. And second one is, when you are taking say same planet you have taken, another natural satellite of the earth is there. So this is say m1, this is say m2. As you have seen, the time period is not depending on the satellite mass, depending on the mass of the what? Celestial object around whom the satellites are revolving. So if I take its time period of revolution is t1, its time period of revolution is some t2. If I take, when I compare here t1 by t2, simply you can write t1 by t2. Why? Because see here m is constant, and moreover this m is not mass of this satellite, mass of this main one around whom they are revolving. So you can directly write t1 by t2 whole square is equal, you can compare the time period simply r1 by r2 whole cube. Okay, this is one point. Another point is, when you compare, listen carefully. So for example, this is sun is there, okay, Mercury is there, Venus is there, Earth is there, Mars is there, Jupiter, Saturn, and all they are revolving here, okay, around the sun. So when you compare, okay, So different planets time periods around this sun, you can directly use the formula directly t square proportional to rq. Why? They are revolving around the sun mass is constant. But when you revolve the satellites time periods around the planet, so this is Mars, this is Earth. Okay, so mass of the Earth and Mars are different. So if I consider planet say P1 or satellite say S1 around Mars, okay, this is M1, around Earth M2, say moon, a moon satellite, you can take anything, natural satellite you can take, or artificial satellites you can take. So yes, two satellites. Now when you comparing, you cannot use direct formula here t square proportional to r cube. This is wrong way of usage. You have to use the formula t square is equal to 4 pi square by gm into r cube. Why I should not use, sir? What is wrong? Can you tell me what is wrong here? Yes, around the same thing you are not comparing, man. Okay, this planet P1, planet P2, planet, when you are doing this P1, P2, P3 time period around the sun, yeah, you can go straight forward this one. But when you are considering the satellite S1 as a time period, when you are comparing around another planets here, masses are different or not here. That's why you should write here T2 by T1 whole square is equal inverse relation with mass. So M1 by M2 into, okay, R2 by R1 whole cube. This formula you have to use. I hope I am clear how to use which formula. Okay, this is what Kepler's third law. Clear everyone? अरे पलकन रहा को दिया. Hello, madams and sirs, Manavas and Manavis, ఏమైనా వింటుండ్రా? ముకంబిక, గాయత్రి, అన్విత, ఆయుష్, కృతి, లక్ష్మిశ్రీ, చరిత్, ఫనీ, కీర్తికా రెడ్డి
Yes, sir.
వింటుండ్రా? ఆదిత్య, తనోష్,
Yes, sir.
Yes, sir.
సౌమ్య, నిఖిల్ శర్మ, ఓం స్వరూప్, భరత్ రెడ్డి, ప్రణీతా గౌడ్, లింగ హరీష్, పరిణీతా గౌడ్, ప్రవార్, are you listening? Yes, Ray. Jaychandra, Shriya, Ashrita, Chandana, Dakshita, Saket Reddy, Shiva, Sahiti, Pranati, Sai Kishore, Suchir, Avinash. This last 3-4 students, they didn't join with audio only. Formalities are just revision నడుస్తుంది, అకాడమిక్ ఇయర్ అయిపోయింది, ఏముంది ఈ రివిజన్లో? బాబు ఈ రివిజనే మీ యొక్క ఫ్యూచర్, అది మర్చిపోకు నువ్వు. ఓకే, yeah, t square proportional to r cube when you have to use, and t square is general formula is 4 pi square by gm into r cube. Okay, when you are comparing around the same celestial object time periods of different satellites, t square proportional to r cube. But when you are comparing the time periods of different satellites around different planets, then the ratio formula t2 by t1 whole square is m1 by m2 into r2 by r1 whole cube. Okay, this is Kepler's third law of planetary motion, conservation of angular momentum and all. Now, sometimes we have satellites like geostationary satellite. What is geostationary satellite, right? Yes, geostationary satellite is a satellite whose what? Time period is equal to time period of the Earth. Yes or no? Geostationary satellite means with respect to Earth, it always looks like what? Stationary. So when I have for example, Earth is revolving around its own axis, how much time it takes, right? 24 hours. If near the surface of satellite is there, if this time period also, if you launch at a particular distance from the center of the Earth such that its time period also equal to time period of the Earth, then they always looks like stationary. This kind of satellites are called geostationary satellites. Now, as you know, the formula t square is equal to 4 pi square by gm into r cube, where radius of this particular geostationary satellite from center of the Earth, if I consider, okay, this height of the orbit from surface of the Earth is h. So this distance small r is equal to capital R plus h. So you can write r square cube here. Or average radius మనం ఏమనుకుంటామంటే దీన్ని r అనుకోవాలి, అప్పుడు మీరు ఇది r అవుతుంది. So now if you see, this is mass of the Earth. You know, mass of the Earth, everyone knows 6 into 10 power 24 kgs, we know. Okay. Now, if you substitute g value, all of you know, gravitational constant value is 6.67 10 power minus 11 Newton meter square per kg square. You substitute these values, right? And when you simplify for this r value and time period of a geostationary satellite, we know 24 hours. Okay, so if you convert into 24 into 60 minutes into 60 seconds one day, that comes out to be 86,400 seconds. Substitute the value of t here, 4 pi square, g value known to you, mass of the Earth. When you calculate for r, this r approximately comes out to be some 42,000 kilometers. As you know, radius of the earth is some 6,400 kilometer approximately, and this is small r is equal to r plus h. When you calculate height above the surface of the earth, height of the geostationary satellite from surface of the earth, మీరు కనుక్కున్నట్లయితే ఇక్కడ ఎంత వస్తుందిరా 42,000 minus 6,000 నియర్లీ 36,000 kilometers వస్తుంది ఇది. Therefore, the height of geostationary satellite from surface of the earth is of the order of how much? Some 35,800 and కొంత చేంజ్ వస్తుంది మీకు నియర్లీ ఎంత తీసుకోవచ్చు మనం. You can take 36,000 kilometers is the height of what? Geostationary satellite from surface of the earth. From center of the earth nearly 42,000 kilometers. Okay, this is what Kepler's laws: first law, second law, third law, planetary motion. So planets are revolving around the sun elliptical path. What making them to revolve like that means the gravitational force of attraction between planet and sun making them to revolve, which provides necessary centripetal force. And we have seen orbital velocity of a satellite also we have seen, which is equal to root gm by r we have seen, isn't it? So we got derivation already. So then time periods also we have compared. Okay, so the questions you should be able to answer on that too. Okay, we'll take after finishing entire thing. Yeah, now coming for, now we'll go for Newton's law. Now we know, so what are the Kepler's laws? Planetary motion, satellite we have seen, geostationary satellite, small theory of satellites you can go through. What are the purpose, usage of satellites for weather forecasting, okay, detecting the ores or the mines and all, forecasting of rains and all, okay, for fluctuations in the atmospheric conditions. And we are using satellites for mobile communication, telecommunication. Okay, so many applications we have for what? Satellites. Once you go through the theoretical part you can read it. Okay, you know much better than us. Now coming for, now which the main governing principle around the planet sun, around the sun planets are revolving is gravitational force. So the scientist Newton, so he gave the mathematical formula for what? This Newton's law of gravitation for gravitational force. Okay, Newton's law of gravity or gravitation as you wish. So how to apply for different objects and all we'll see now. See Newton's law, what he says no. So whenever you have, see this law is strictly applicable for point masses. If I have a point mass m1, under point mass here m2, say if I take reference origin in the space somewhere else, this is x-axis, this is y-axis, position vector of first particle is r1, position vector of second particle is r2, separation between them is some r. Okay, if I consider, see if I fix m1, if I ask you where is position of 2, this is position of 2 with respect to 1. If I fix m2, if I ask where is m1, so you'll finger right like this, no, you will direct your finger like this. So position of 1 with respect to 2. Of course their magnitudes r1 2 is equal to r2 1 is some r. So now if I consider, so this particular body attracting this body, so force on this 2 because of 1 is like this. Similarly this 2 body also attract this first body, this is force on 1 because of 2. Are you following? So the gravitational force of attraction, as we know, have seen already, proportional to m1 m2 proportional to r square g m1 m2 by r square, saying this is the magnitude of gravitational force which acts along line joining their centers. I am not touching topic newly, I am revising, keep in mind. So if I write in vector form, if I consider, say these 2 points are there, this is m1, this is m2. If I consider force on 2 because of 1, this is like this. Position of 2 from 1 is this one, so position of 2 from 1. So if I write in vector form, this is g m1 m2 by force on 2 because of 1, because of 2, okay, force on 2 because of 1, g m1 m2 by r, distance of the 2 from 1, that is r2 1 square, and direction how it is r2 1 square, direction how it is towards m1. So this is which is opposite to r21. That's why we mention unit vector for direction. Opposite to r21 unit vector is minus r21 cap. R21 is like this. R21 cap also like this. Force is opposite to this one. That's why minus r21 cap. So as you know, the definition of a cap is a bar by mod a bar. So I can also write this one as minus g m1 m2 by r2 1 square into r2 1 cap is r2 1 bar divided by r2 1. Hello, what you can write? R2 1 bar, r2 1 bar by r2 1. So you can also write in vector form simply as minus g m1 m2 by r12 cube into r12 bar. This is the force on second particle because of first particle. Following all of you? This is how Newton's line vector form. Similarly, if I ask you, what is the force on 1 because of 2? Force on 1 because of 2. So 1 is here, 2 is here. because of 2, force on 1 is like this, force on 1 because of 2. Position of 1 from 2 is in this way, position of 1 from 2. So now write down here, now what you can write, G m1 m2 by r square. Position of 1 from 2 is r12 square into up direction of is opposite to r12 cap here, that is minus r12 cap. I can also write minus G m1 m2 by r12 cube into r12 bar. Therefore, this is force on 1 because of 2 in vector form. This is Newton's law of gravitation in vector form. It is applicable strictly for point masses and is force acting along line joining their centers. Okay, so which is always attractive in nature. Okay, sometimes we can also say this Newton formula. This negative indicates that force on 1 because of 2. Force on 1 because of 2, how it is, right? Like this, no? What is the meaning of this one? Position ku opposite గా ఉంది అంటే ఏముంది ఈ డైరెక్షన్ లో ఉంది టువర్డ్స్ 2 ఉంది టువర్డ్స్ 2 అంటే minus indicate that 2 is attracting 1. In gravitational meaning is what? 2 is attracted to 1 or here 2 is bound. Okay, what here, so on 1 you are talking like this force, no, this is 2, this is 1, so this is force on 1 because of 2, its position is position of 1 with us 2 is like this, so this is bound by gravitational force of attraction. Okay, that's the meaning of your negative symbol. Now fine sir, you are saying that Newton's law of gravitation is applicable for point masses, so what about extended objects? Say for example, if I ask you the question, a point mass, a spherical body is there here like this, and a rod of uniform, okay, density and length L is over here. So this first end of the rod is a distance of some A, and second end of the rod is a distance of, say for example, B. Length of the rod is L, so L you can write simply B minus A. So if this mass of this particular point mass, say small m, so this is small m and this is a capital M, what is force of attraction if I ask you? How do you find out? Yeah, sir, direct formula, sir. What is there? F is equal to G m1 m2 by r square. Okay, fine, good. Directly, that is equal G m1 m2 by separation between them. Which I have to take? I have to take A, or I have to take center of the rod, A plus L by 2 I have to take, or I have to take A or B I have to take. What I have to take? Why? Why? Because see, this section of the rod is at this distance. This section of the rod is at this distance. So which I have to take? There is no particular meaning. You cannot apply directly. Why? Yeah, you can see that Newton has proved that any symmetrical body can be assumed that its mass is at center of mass m. Okay, fine, point mass. Sir, why I should not take that this is made up of center of mass? Okay, you cannot take like that. Symmetrical bodies కి simply తీసుకోవచ్చు. ఇది కూడా symmetrical body, entire mass you can assume, but you cannot treat only spherical body entire mass can be taken. Why? Results are matching, that's why you can take. But here results are not matching. Practical is different, situation is different. Okay, therefore we cannot take entire masses here. So what you have to do now, first this kind of thing, as it applicable point masses, anyhow this can be treated as a point mass. By calculus he has proved it, you can assume that it is made up of large number of layers of thickness r and dr. Okay, when you integrate, no, same answers are coming. So but this rod you divide this into small elemental masses ga divide cheyali, small pieces, very small, dx, very small. Then take one such kind of small elemental length dx at distance x from this point mass, then find the force of attraction between them, or say this point mass exerting force on this dx element like this, which is force is df here. So you can write g m1 m2, m1 is small m, m2 is mass of this element is say dm divided by x square. So if m is the total mass of uniform rod length L, what is the mass per unit length? That is m by L. What is the mass of dm? Mass of dm will be this is gm by x square. Mass of dm length is m by L and its length is dx. This is the df. And integrate you have to do, no? So see, if this element is at distance a, means element will be over here. This x element at x distance element. If this element is over here means length is a, separation is a. If this length element which I have taken dx extreme end undanko, then x will become is equal to b, x will become to b. Okay, so limits of this integration vary from A to B, so that all elemental mass forces on this mass element like this force, on this also like this, on this like this, on this like this, on this like this, all are added up. Summation means integration. So from where to where? So integration df some values come as what? F here. Okay, so limits from A to B. If you simplify, what will you get? Ray? G capital M small m by L integration of x square. Okay, x square 1 by x square. 1 by x square means x power minus 2. This is dx, limits will be from a to b. This becomes what again round? G capital M small m by L into integration of x power minus 2 is minus 2 plus 1 by minus 2 plus 1 minus 1 by x. Okay, this will be A to B. So if I simplify this expression, force on this particular rod of uniform length L, okay, because of point mass is minus G capital M small m by L into upper limit minus lower limit. This minus I have taken already outside. So this becomes 1 by B minus 1 by A. If I take this minus again inside, it becomes plus, it becomes minus. So you can write down G capital M small m by L into 1 by A minus 1 by B. Okay. Now, see, this is the value of what? This is the value of, yes, no, gravitational force because of this point mass on entire uniform rod. With what force? This attracting entire average force is with this much, no? This rod also attract this point mass the same force. They form action reaction pairs. Okay, like this for extended object, by taking the elemental masses, you have to extend the Newton's law of gravitation. Okay, this is how we will find out. And now in next upcoming classes we express the forces in terms of fields and all. So what is gravitational field? Okay, so before that, can you find out one question now? A question, JND. 3 point masses are placed, okay, at distances of vertex of a equilateral triangle. Okay, separation is there, given as separation A. So can you calculate the force on any one point mass? Come and do it. Force on any one point mass because of other point masses. So this can be given by principle of superposition. Vector sum of all the forces cheyali. That is called principle of superposition here. Yeah, but the principle of superposition already in case of electrostatics we have seen, in case of we have seen wave optics, we have seen waves, we have seen net force. So if I take this point mass on anyone is saying, no, you can take this one, you can take, or this one, you can, anyone you can take. So if I take this one for example, so this is one, okay, you can say two, this is three. So on two, if I consider two is being attracted by one like this and also by three like this, the resultant force will be somewhat like this. So net force. So force on 2 because of 1 you have to find out, force on 2 because of 3 you have to find out, and their vector sum you have to take. That is the net force on 1 because of remaining. This is what principle of superposition. So the net force on any one point mass is, it is vector sum of forces due to individual point masses. And one more point here is there. See, these two are there. This is also there. Now force between these two is not affected by presence of this one ray. I'm talking only force between these two, not the net force. Similarly, force between these two is not affected by presence of this one. So the force between any 2 point masses is not affected by the presence of the other particle in its vicinity. But net force definitely gets affected. Net force on this one is because of this one, and net force is somewhat in this way. Okay, net force is going to be principle of superposition. Okay, vector sum of the individual forces. నీకు అర్థమవుతుందా నేనేం మాట్లాడుతున్నాను? ఈ 3 పార్టికల్స్ ఉన్నారా, మీరు ఇద్దరు ఫ్రెండ్స్ ఉన్నారు. మీ ఫ్రెండ్షిప్ వేరే వాడు రావడం వల్ల ఒకవేళ ఎఫెక్ట్ కాకపోతే దట్ ఈస్ యువర్ రియల్ ఫ్రెండ్షిప్. దిస్ 2 ఫ్రెండ్స్ ఆర్ దేర్, another friend also there. So your friendship is very strong. If this fellow is not influencing you, then only your friendship is strong. So friendship between these two is not affected by the, okay, in presence of this particular friend. సేమ్ థింగ్, ఈ రెండింటి మధ్య గ్రావిటేషనల్ ఫోర్స్ దీనివల్ల ఎఫెక్ట్ కాదు, కానీ నెట్ ఫోర్స్ దీనిపైన ఏదైతే ఉందో దీనివల్ల యొక్క వెక్టర్ సమ్కి ఈక్వల్ అని మాట్లాడుతున్నాను. రైట్, వాట్ ఇస్ ద ఆన్సర్? ప్లీజ్ టెల్ మీ ఫాస్ట్. 1 minute టైం త్రో చెప్పండి. జస్ట్ మినిట్, ఐఎమ్ కమింగ్ బ్యాక్. రెడీ విత్ ద ఆన్సర్. Be ready with the answer. Yeah, what is the answer, right? Everyone.
Sir, root 3 gm square by a square.
Root 3 gm square by a square. Very good. See, because of this angle between how vectors is 60 degrees here, equilateral triangle, and this force is equal to this force. When two forces are equal, resultant force, how much is the formula? 2a cos theta, formula, parallelogram law. 2a cos theta by 2, or simply you can say 2b cos theta by 2, as a wish, if a, b vectors are there. అవునా కదా? రిజల్టెంట్ ఫోర్స్ ఇస్ F1 F2 తీసుకుంటే F1 is equal to F2 is equal to F తీసుకుంటే రిజల్టెంట్ ఫోర్స్ ఇస్ గివెన్ బై వాట్ ఫార్ములా? రిజల్టెంట్ ఫోర్స్ ఇస్ గివెన్ బై 2F cos theta by 2 in parallelogram law vectors, and resultant bisects the angle between them. So resultant force is 2F. F means any one force. This also same, this also same. G M1 M2 by r square is a square into cos theta by 2. Theta between the forces is 60 degree by 2, 30 degrees. So 2 gm square by a square, cos 30 is root 3 by 2. So what the answer will get? This becomes root 3 gm square by a square. This is the resultant force on any one particle. Resultant force on any one particle. Similarly, tomorrow in future, he will get any 4 particle CHU, 3 particle UH, you can find out. So any one force, for example, any one, this one if you give. So this force, okay, and also this also, no? So vector sum of these 3 you have to consider. These 2 will be resultant along this ray, equal. Distances equal, I think. And for this, you have to add the force of this one also. And vector sum you have to do. Okay, that you will get the resultant force. Is it clear, everyone? Hello?
Yes, sir.
Yeah, this is how we'll find out what the gravitational force and all. And next we should about point mass type in the extent of principle of superposition, how to do also over. Now coming for what is gravitational field? What is electric field? The region around the charges up to where the charges are feeling influenced by other charges, or this charge is showing influence. That is called electric field. So what is gravitational field? The region around this particular point mass up to where it shows its influence is called what? A gravitational field. Or any other point mass experiences force because of this particular point mass up to where influence is there, no? If I have a point mass, so up to here it may show its influence, no? Strictly speaking, any point mass influence will be up to infinity. Of course, it may go on decrease. Okay, so it a certain region is there around it up to where it shows its influence, or any other point mass coming in this region will experience the force. That is called gravitational field. Okay, how to measure the intensity? Intensity of gravitational field E is measured as how much force per unit mass. Okay, that is what intensity of gravitational field. So any point mass if you bring here, so m dash say or m naught, you can say how much force right here? G m naught by say distance is r, that is r square. This is the force. But the intensity of this point mass at this particular point and a per unit mass, G m naught by r square divided by m naught share. Therefore, E is equal simply Gm by r square. Okay, fine. This is what gravitational field intensity, and we also this one we call acceleration due to gravity. Also we call both are same meaning. So force experienced per unit mass. Very simple, Ray. For example, this Earth is there. So in the vicinity of the Earth, when you release a small point mass, okay, its height is very small అనుకుందాం, రేడియస్ కంపేర్ చేసుకుంటే నియర్ ఉన్నట్టే కదా. సో కాబట్టి వాటి మధ్య see I can take this one as nearly to the surface of the earth అన్నట్టే. So this is radius r, this point mass. So I can separate by Newton's assumption. He has proved that any symmetrical body can be assumed to be placed at the center of mass whose mass equal to its own mass. This is capital M, this is small m, separation is r. So the gravitational field between them, the value of intensity of gravitational field now, G capital M small m by r square per unit mass, no, by m. How much this is? Gm by r square. R means here capital R. This is what value of G? Yes or no? Intensity of gravitational field anna. Okay, gravity acceleration due to gravity anna okate meaning. Okay, so G is equal Gm by r square formula. This is near the surface of the earth. Near the what? Surface of the earth. So the gravitational force per unit mass is known as gravitational field intensity or acceleration due to gravity. So if I consider the field because of this point mass at a particular distance, okay, if I imagine a unit point mass is given by formula Gm, if I take this as capital M, small m, this goes to Gm by r square. How the force direction is towards this one, like this distance is r. If you want it in vector form, this vector form will come, how much the vector form will be? This will be Gm by r square. Okay, magnitude. So position is r bar like this, direction is in this way. So if I write position force, this is force direction, this is position direction. So force and position are opposite, no? So I can write minus r cap, then it becomes minus Gm by r cube into r bar. Okay, this is gravitational field intensity in vector form. Negative indicates it is toward that point mass, which indicates attractive force in nature. Okay, so magnitude of the gravitational field intensity because of a point mass at any distance is given by Gm by r square. Is it arthamainda? So for Earth and mass system, when you are talking here, Earth and mass particle system, when you are talking, So this itself is called acceleration due to gravity near the surface of the earth is ggm by r square. If you take this value 6.67 into 10 power minus 11 into 6 into 10 power 24 by radius of the earth is 6200 kilometers mean 10 power 3 meter whole square మీరు చేసినట్లయితే nearly we are getting 9.8 meter per second square. So near the surface of the earth when heights are very smaller than radius of the earth, whatever the acceleration is produced in this particular body because of gravitational pull of the earth is known as acceleration due to gravity. G is equal gm by r square. Okay, how it is varying actually with distance, you know very well. So gm by r square, if I take here, this is g, this is m, any point mass, center to center distance is r, this r is equal to r plus h. When h is very small, then only you can take r is equal to r near the surface of the earth. So if this planet is of uniform density rho, its radius is r. Okay, so you can write this value as gm by r square can be written as g by r square. This is g ray. Mass is density into volume. Volume is, if I assume earth as a perfect sphere, 4 by 3 pi r cube. This becomes 4 by 3 rho z r. So g value is what? Proportional to what? R. If you take r small r, linearly varies from center. Okay. So if I draw the graph for g value, for this is linearly varies with center. If I take small r, small r diskunte, and from outside, okay, outside the radius, inside value of g varies linearly. Outside what happens? More than r. It follows what kind of form here? G is equal to gm by r square. The maximum at surface of the earth undi. As r increases, it becomes this kind of profile, decreases, rectangular hyperbola. Sorry, square g proportion, not rectangular hyperbola. I'm sorry, 1 by r square profile. This is how g varies. So this is at r is equal to r, and where then finally what happens? G is having inverse relation. Okay, this is what intensity of gravitational field, acceleration due to gravity near the surface of the earth. Okay, now from center of the earth intensity is varying linearly and చెప్తున్నాను. Again I will be deriving this one later, keep in mind. Okay, so now after this, how variation value of g acceleration due to gravity near the surface of the earth. Later we'll see for different bodies ray, spherical body మనం మాట్లాడతాం general గా. So if I consider g value here, okay, this much. Now at a height, any height, if you consider variation of value as height and depth we are talking, no. So at a particular height, say surface of the earth radius is r. On the surface we know value of g is equal to gm by r square. Okay, this is small r is equal to capital R. Any other height, if I take the body, it will be pulled by earth, no, isn't it? So what force it will be pulled? Actually g capital M small m by, so total distance if I take a small r, that is equal to r square. So what is g value? Actually force per unit mass, this is equal to gm by r square. This is equal to gm by r means here r plus h whole square. This is the value of g at any height. Okay, this is called gh. If I divide gh at height and g on the surface, this is gm by r plus h whole square. On the surface is gm by r square. This becomes r square by r plus h whole square. This is more general formula for g, always you can use. That is r by r plus h whole square. R by r plus h whole square. If you see here, r is more or r plus h is more, r plus h is more. So as height is increasing, acceleration to gravity value is decreasing. And we make a small approximation here. What approximation we'll make here? When height is very smaller than radius of the earth, then by binomial expansion, so we use this formula gh is equal to g into, we take numerator r by r plus h, now take r common here, and denominator 1 plus h by r will get 1 plus h by r. What is there? Square is there. This to get cancelled. So g into, I will get 1 plus h by r whole power minus 2. See, h is very smaller than r. So h by r is very lesser than 1. So whenever in binomial expansion 1 plus x whole power n, when this mod x value is very lesser than 1, I can use the formula 1 plus nx. So here z into, this is x value which is smaller than 1. So 1 plus nx, 1 plus nx, n means minus 2 into x means h by r. This is what? but only for very smaller heights of the order of few meters, maximum 1 kilometer, 2 kilometers, 3 kilometers. Okay, but not comparable. What is the radius of the earth is 6,200 kilometers. You should not say 1,000 kilometers, 10,000 kilometers. No, very, you should not use this formula, not valid. Why not valid? Just take one example, I will answer you. So find the value of G, write the question. Find the value of acceleration due to gravity, value of G at a height half of the radius of the earth. At a height half of the radius of the earth. Yeah, come on, tell the answer, right? Find the value of G at a height half of the radius of the earth. Or also you can write one value, you can also write here. Yeah, H is equal to R by 2, no? You can find it out. Yeah, చెప్పండి answer చెప్పండి ఎంత వస్తుందో. Everyone, can you hear me? Hello.
Yes, sir.
Yeah, please tell. If you use this formula, what happens, Ray? GH is equal to G into half of the, why you should not use, why you should use. Let us see. H value is R by 2. 1 minus 1 is 0. At a distance equal to half of the radius of the earth, okay, above surface of the earth, the value is coming G, but practically the value of not actually 0. It has some value. And why this answer is not matching? Correct only, no sir. Why correct? It is not correct. Why? Why? Because H is equal to, I use the condition very small. Here H you are saying of the order half of man comparable. You should not use this formula, approximate formula you should not use. What formula you have to use? GH is equal to that formula, man. G is equal to GM by R at a height is equal to, direct you can use R plus H whole square. Or if you want to compare GH by G, as G is inverse relation, no, general formula on the surface of the earth is R square. G inverse to R, no, GH by G is equal to inverse relation. What you can write? R by R plus H whole square. Okay, so G into R by R plus H value enta ikkada? R by 2 whole square you have to use. Yes or no? So G times now R square by 2R plus R is 3R by 2. 3R by 2 means 9R square by 4. 4 goes up. This is equal to 4 by 9 into G at height. Sometimes you'll ask percentage change rate. You calculate change, man. GH by G, you know, that is 4 by 9. Either side do minus 1. GH by G minus 1 is 4 by 9 minus 1. So GH minus G by G is minus 5 by 9. Minus indicates value of G is decreasing. This is change in value of G by original value. If I do into 100, it gets percentage change, which is decreasing. 5 by 9 into 100. Okay, what are the value you get? That is the answer. So minus indicates value of G decreasing. This is called percentage change. This is called what? Percent. This is what value of G with height. Okay, and value of G on the surface. At the depth also you can find out. Following everyone how to use the formula. In Babu. Yes, everyone.
Yes, sir.
Right. So shall I go ahead? Shall I go ahead? If you write this question. We're talking G values, gravitation field, gravitational intensity on the surface of the earth, GM by R square, how much its value surface at a height H. We are writing the variation value of G with depth from center of the earth varying linearly, outside is varying inversely, G proportional to 1 by R square graph. Okay, and at a heights and values is and binomial approximation you have seen, and then why you should not use the formula for approximated heights, equal heights, comparable heights. Okay, so that value we got, and we also found percentage change in the value of G. Okay, next with depth we see. Shall I go ahead?
Yes, sir.
Yeah. So if depth see, all of you listen carefully. So this is solid earth, uniform density anukunnam. You are going in depth D here. When depth D is gone, this distance will be how much, right? R minus D. Right. So as we have seen, G value is also in terms of GM by R square If this is uniform density, we wrote mass is density into volume, and then we have derived the formula G is equal to 4 by 3 pi rho G R. So G at any depth, I can write down this one as, see at any depth ante, ikkada chusukunnatlaithe meeru, I can assume that that value at this point you want, at depth of D. I can assume that this is on a sphere of radius R minus D from center. This is D ante in the R minus D. So GD at that location I can write down as for uniform density 4 by 3 pi rho G into R minus D. If I divide GD by G, 4 by 3 pi rho G, 4 by 3 rho G, it cancels. So I will get R minus D by R. So GD becomes G into 1 minus D by R. Okay. If I ask you at a depth of radius, how much, that means you are at center. At depth means you are going to a depth equal radius means where you are at. You are at center. D is equal R. Value of G at the center is 0. Value of G at the center is how much? 0. What is the meaning of G at the center is 0? So acceleration to gravity means force because of earth. So different section of the earth, they are equally pulling it in from all directions. You can assume like that. So net gravitational force 0. Net gravitational force is 0. Gravitational field intensity, which we call acceleration to gravity, also 0. When net force is 0, that's the meaning of it. And one more way of thinking, upper hemisphere pulling exactly with what force applying, lower hemisphere also like this. Our right side hemisphere with what force pulling? No, left side hemisphere also pulling the same force. Net force is equal 0. Or if you make 4 parts, this part force, this force balancing, this part for this part for balance, anywhere on coach meru, net force is equal 0. So what is the weight of a person at center of the earth? That is equal to 0, not mass 0. Effective weight, this is called weightlessness condition. Weightlessness condition, that means if you go to a center of the earth, if you're standing on a weighing machine, normal reaction measured by it is 0. Or if you're suspending a pendulum block at the center of the earth, okay, so the time period formula of a pendulum bob 2 pi root of L by G. G is 0 there, so time period is infinity. Time period infinity, it takes infinite time for one oscillation. That means it will not perform oscillation. That means it is at rest. Whatever the position, you can keep it comfortable. Okay, at the center of the earth, look at me. At the center of the earth, pull the shanko. It has to oscillate. No, when you pull it, restoring force itself is not acting, man. When you are deriving the oscillation derivation, mg sin theta is restoring force. Here, mg sin theta itself is 0, no restoring force. Definitely, it will not come back. It will not oscillate. The way of saying is that it will oscillate after infinite time. Means it not oscillate. For example, you have taken money from someone. Yes, I will give, man, after some time. The time will never come, he will never give you. And the time will not come, it will not oscillate here. That is the meaning of time is equal to infinity here. So time, but because if you put the bob here, no, it remains here only. No restoring force. If you pull the bob here, it will here only. So each and every position is more comfortable. A position this one alage untadi. So at the center of the earth you have gone and you have poured some water like the space like this. Whatever the position of water, it stays there only. Why? There is no gravity to pull it down. And in glass of water, you have kept water in the glass of water. Okay, 1 minute. Right? Glass nankunam. So if you pour like this, okay, even though water is there, it will not come outside. If you sprinkle like this water, what happens now? It will, okay, whatever the position you have given, it remains there, right? There is no restoring force, no gravitational force. That is the meaning of weightlessness. So you can also what? You can just height you are saying, you will like that only. If you are like this, like that only. Okay, each and every position is more comfortable. No force is acting at all, man. That is the meaning of weightlessness. Okay, that is what in case of center of the earth, value of G depth is okay 0, and at any depth from surface of the earth is equal GD is equal G into 1 minus D by R. And one more question they're asking the gravitation here. When I place at certain distance, it performs simple harmonic motion. Look at the board, everyone. So this is the R at a depth D. This distance from center, if I take R minus D. So if I imagine a point mass here, okay, on this small sphere of radius R minus D, this point mass experiencing force like this, and its position is R minus D in this way. And G value you have seen, G value is equal to GD at a depth. D is equal to G into 1 minus D by R. So G into R minus D by R. This is GD. In vector form, if you write now, this towards center of the earth. So minus G into R minus D by R. This is on the surface of the earth constant. Radius of the earth is constant. This value is GD. So acceleration type. Acceleration proportional to minus X. X के प्लस में क्या है यहाँ R minus D. See from center of the earth, if I consider this is position X. How much position x from center ray? R minus d. So it is satisfying the condition of what? SHM. So it performs what? SHM. So A proportional to minus x. When you compare this value of GD magnitude wise minus and Chandra. So R minus D into G by R. So if you compare this with standard equation of SHM minus omega square x. This is x from center. So omega square plus में कितना है value? G by R. So omega will be how much now? Root G by R. This implies omega is 2 pi by T is equal to root of G by R. Therefore, time period of oscillation of this particle which is placed at distance of say depth D is equal to 2 pi root of G by R. With this time period it oscillates how? Simple harmonically. With this time period it oscillates how, sir? It oscillates simple harmonically. This is the variation value of G with height and depth at different locations and all. Now, so gravitational field intensity because of point mass we have seen. What the formula we have seen? Point mass extension now I'm doing. If I, because of spherical shell if I take or sphere if I take of mass m at this radius is r at any point I want, I can imagine the entire mass is at center of mass at distance is equal to small r. If I imagine unit point mass, force on this one is gravitational field intensity F by m. F by m naught, how much you got a value? That is gm by r square. Gm by r square, r more than r. So this is gravitational field intensity because of a spherical distribution of mass at any outside point where r is more than radius. On the surface, E at surface, r is equal to r. Substitute there, gm by r square. At any interior point, what is the value of gravitational field intensity? So how do you do this one? This we do like this formula, gm by r cube into r. Gm by r cube. This entire value is constant. So already I mentioned this ERG proportional to Laundra R only. Therefore, so we can prove it. How we can prove this one? We have to derive this one. Okay, ఆ derivation ఇప్పుడు అనవసరం lengthy parts మనకు అవసరం లేదు. Results గుర్తుంచుకోవాలి మీరు. If it is a casual teaching, I would have done. So already we have done this part for you. Just I am recalling the points. ఎట్లా చేసుకోవచ్చు దాన్ని? What is gravitational field intensity at any particular point at distance r if I want? You take this r as radius and construct a sphere of radius small r. Okay, sphere of what? Radius small r. That at this point P, net gravitational field intensity is because of this sphere of radius r as well as what? Because of this outer shell of radius r minus r. Okay, when you two fields when you are calculating, or one more way of doing is, so at any distance x from center if I consider, just I am going for ఈ formula గుర్తుంచుకోండి మీరు ప్రస్తుతానికి. And see here, if I put r is equal to r, see the formula, gm by r square will come. If I put r is equal to 0 at the center, E will come out of 0. Already we have seen these results. At the center, intensity of gravitational field or acceleration due to gravity is 0. At the surface, gm by r square we have seen. So this formula is satisfying. So at any interior point of the solid sphere, okay, a distance r from center, okay, as it's varying linearly, the formula for intensity of gravitational field, very, very important, gm by r cube into small r. ఇది గుర్తుంచుకోండి. Derivation at least just I will be telling you like this. So if I consider, మీకు అవసరం లేదు, but way of doing I am telling you. This is radius is r. At any particular point, if I want P at distance x, okay, from the center of this spherical shell, at distance x. Okay, so I will do here what, so I will actually take a small spherical shell of radius r and width dr. Okay, width dr, and I can assume that, okay, so the gravitational field intensity, okay, because of this I can take this one as smaller radius width dr. Okay, so this point P will become on this spherical shell it is, and the formula because of field shell or a body is equal gm by r square, you know very well, gm by r square. R square means how much right here? That is x square. This is mass of x portion. Mass of x portion, how do we do? Entire mass m is in the volume 4 by 3 pi r cube. Unit volume, how much mass? M by 4 by 3 pi r cube. So dm mass how much? So here m by 4 means 3 pi r cube into volume of this element you have to take, of radius what? Small r. So this becomes 4 pi, okay, 4 pi what or x మీ ఇష్టం 4x తీసుకుంటే x r తీసుకుంటే r నన్ను ఏదైనా తీసుకోవచ్చు 4 pi x square. If you take x, take width dx. If you take smaller, take width dr, man. 4 pi x square into dx. This is the mass. Substitute over here that dE comes out to be g by x square into is మొత్తం substitute చేసుకోవాలి 4 pi 4 5 cancel అయిపోతుందిరా ఎంత మిల్ చెప్పండి ఇప్పుడు సో 3m by r cube into x square, okay, dx. And when you integrate this one under what limits here? So we want for the spherical shell at this point P, a distance r అనుకుంటున్నాం కదా. Okay, so x value vary from where to where at any point మీరు తీసుకుంటే ఇది x దగ్గర తీసుకుంటున్నారు. So this limits vary from x to what at x to r or simply 0 to r తీసుకోవచ్చు మీరు తప్పండి 0 to r directly you can take. Why? Because x అనుకుంటున్నాం కదా, any distance r will get. And integrate, the result will come out to be gm by r cube into x. And distance x from center. If it is r from center. Hello, వింటున్నారు అందరూ what I am talking?
Yes.
Entire gravitation is similar to electrostatic chapter. మొత్తం ఈ చాప్టర్ యాజ్ ఇక్కడ గ్రావిటేషనల్ ఫీల్డ్ అంటాం, అక్కడ ఇంటెన్సిటీ అంటాం. హియర్ గ్రావిటేషనల్ ఫీల్డ్ బికాస్ సాలిడ్ స్పియర్ అంటాం, అక్కడ ఇంటెన్సిటీ ఆఫ్ ఎలక్ట్రిక్ ఫీల్డ్ బికాస్ ఆఫ్ నాన్ కండక్టింగ్ డిస్ట్రిబ్యూషన్ ఆఫ్ చార్జ్ అంటాం. అంటే మనం చార్జ్ ని ఇట్లా వాల్యూమ్ లో పెట్టామనుకుందాం. ఇఫ్ యూ ఆర్ కాన్సన్ట్రేటింగ్ దిస్ చార్జ్ ఇన్ ఏ స్మాల్ వాల్యూమ్ అనుకో, సో ఫీల్డ్ అట్ ఎనీ పర్టికులర్ డిస్టెన్స్ ఎక్స్, ఇంటెన్సిటీ ఆఫ్ electric field is given by formula. ఇక్కడ g బదులుగా అక్కడ 1 by 4 pi epsilon naught, ఇక్కడ క్యాపిటల్ M బదులుగా q x by r cube వస్తుంది మీకు as it is. This is g. Okay, so see here జాగ్రత్త చూడండి, ఇక్కడ gm by r cube into x అని పెట్టాను కానీ ఇంతకుముందు where I have used the formula. Yeah, gm by r cube. G means 1 by 4 pi epsilon naught, m means q, r cube means r cube, x means x. As it is electric field తీసుకుంటే because of non conducting distribution of charge 1 by 4 pi epsilon naught qx by r cube. కావాలంటే పోయి చెక్ చేసుకోవచ్చు. This is intensity of gravitation, intensity of electric field, force per unit charge at a distance x in a spherical distribution of charge. Here what? Mass distribution here, gravitation ante gm by r cube. That's why if I consider the intensity or gravitational field value from center to certain distance radius, it varies linearly and then it falls like this. This is what gravitational field intensity at a particular point inside the spherical, inside a sphere, inside a what? Inside a sphere. Following everyone? Yes, students. అరే చెప్పండి రా కొద్దిగా, నేను మీకోసం కష్టపడితే నాకు రెస్పాన్స్ కూడా ఇవ్వట్లేదు. ఐఎమ్ రికాలింగ్ ఆల్ ద కాన్సెప్ట్ ఫర్ ద సేక్ ఆఫ్ యూ పీపుల్ అండ్ యు ఆర్ సింప్లీ డమ్. ఒత్తుకోరా బై ఒర్లుకో నాదేం పోయింది. సి ఇఫ్ యూ డూ లైక్ దట్ నో, సింప్లీ ఐ విల్ సమ్ ఆఫ్ ద ఫార్ములాస్. నాట్ ఇంత టెన్షన్ తీసుకోవాల్సిన అవసరం నాకెందుకురా. దెర్ షుడ్ బి రెస్పాన్స్ ఫ్రమ్ యూ మ్యాన్. నేను ఇంత స్ట్రగుల్ తీసుకొని మొత్తం చాప్టర్ ప్రతి కాన్సెప్ట్తో పాయింట్ టు పాయింట్ చెప్తూ ఉంటే ఒకడు రిప్లై చేయట్లేదు, ఫార్ములా చెప్పట్లేదు. మనం కూడా ఏం చేస్తాయా gm by r square gm by x cube గ్రాఫ్ ఇలా వస్తారా, ఎస్ ప్లీజ్ గో అహెడ్ రివిజన్ అండ్ ఆల్ ద డౌట్స్ అంట. అది కాదు కదా పద్ధతి. అంటే మీకు ఎట్లా చెప్పినా కూడా కష్టమైనట్టు, అంటే ఎట్లా చెప్పినా ఉపయోగం లేదన్నట్టు. దట్ ఇస్ ద మీనింగ్ ఆఫ్ దిస్ వన్. ఎస్ క్లియర్ దిస్ వన్?
Yes, sir.
Yes.
Yes, sir.
Yeah, gravitational field intensity. Now one more point, we'll talk spherical shell ray. In place of spherical shell we can use shell theorem here. Gravitational field intensity కోసం మనం ఏం మాట్లాడతామంటే స్పెరికల్ షెల్ గురించి మాట్లాడుతాం రా. సో మనం స్పెరికల్ షెల్ దగ్గర ఏం మాట్లాడతామంటే ఐ విల్ డ్రా ఫస్ట్ ఇక్కడ తీసుకుంటా ఆగండి, ఇక్కడ స్పేస్ తక్కువ. ఓకే, ఐ విల్ రిమూవ్ దిస్ వన్ హియర్, దిస్ పార్ట్. Yeah, gravitational field intensity inside a spherical shell. Gravitational field intensity inside a spherical shell. That is also called shell theorem antam. Okay, what does this shell theorem indicates? You see, we can prove it also by shell theorem, right? Say for example, I have a shell, means inside there is no mass. The shell of some thickness is there. Okay, if I take any particular point, say here, I want the gravitational field intensity because of this particular spherical shell. Okay, if I imagine unit point mass here, so this particular portion, actually see, you just draw points from this one like this. intercepting this region. Okay, and this also intercepting over here. I want this. So what is the field because of this one? You have to calculate. Or e portion this coach, e portion this coach, e portion this coach. Okay, what does shell theorem indicates? The gravitational field intensity inside a shell is equal to 0. So why? Because if you calculate, see, your mass is distributed on the area, surface area, local mass లేదు, volume లేదు. So you can write 4 pi r square, or radius 4 pi r square distance. So here, this particular, if I take a point mass, if I consider, okay, if I draw lines from it, they're intercepting this, no, this area mass kanukochu, this area mass kanukochu. So the average distance of this one from this element is r1. So this is m1. This distance I can take as r2. This intercepting length of mass is m2. So if I write m1 by m2, if I write proportional, a1 by a2. A1 means depends on radius, area. See, mass depending on the area. This is intercepting more area. This enter lesser area. You can any point mass inside. If you take and if you draw the lines, they are intercepting on the spherical shell like this. So this region mass definitely more. Why? This area is more. This region mass definitely less. Why? Area is less. I can simply write down this one as r1 square by r2 square. Okay. Fine, everyone. Now, if we write this mass ratios R1 by R2, you can show that. So how you can write down here intensity of gravitational field? You can calculate point mass. So this mass M1, no? So gravitational force because of this particular region, you can write down now G M1 M2 by R square. G M1 unit mass gabatti M0 by R1 square is equal to, see, I'm going to calculate this forces, the ratio of force I will take here. Okay. So if I take this one as F1 and another I will take as F2, I will take, and I'm going to find out the forces, how they vary. So G, M, so this portion with what force is attracting like this? G, M2, M0 by a distance, say for example, R2 square. Okay, if I take the ratio of these forces, F1 by F2, G, M0, M0 cancel. We are getting m1 by m2 into r2 square by r1 square. If I take the ratio of forces by this shell theorem calculation, m1 by m2 proportional to what, r1 square by r2 square into what we have here, r2 square by r1 square. Cancel 1. That implies f1 is equal to f2. That means inside a shell, if I take any particular point, okay, so any etline this one mirror interior diskunte, for this point mass at this point, if I imagine unit point mass, this region of the shell with what force attracting F1, this region also attracting with the same force. Why? A distance is less, a distance is more. Such that the entire distribution occurs such that net force is equal to 0. That's why intensity of gravitational field inside a spherical shell is 0. అట్లనే కాదు ఎక్కడ తీసుకో ఈ పాయింట్ నుంచి లైన్స్ ఇట్లా డ్రా చేయటు ఇట్లా డ్రా చేయి. సో ఈ రీజియన్ వల్ల ఫోర్స్, ఈ రీజియన్ ఫోర్స్ క్యాన్సిల్ అయిపోతుంది. సో నెట్ ఫోర్స్ ఇస్ ఈక్వల్ టు 0 వస్తుంది. దట్స్ వాట్ ఇంటెన్సిటీ ఆఫ్ గ్రావిటేషనల్ ఫీల్డ్ ఇన్సైడ్ ఎ స్పెరికల్ షెల్ ఇస్ ఈక్వల్ హౌ మచ్? ఇస్ ఈక్వల్ టు 0. అండ్ దేర్ఫోర్ at any interior point the gravitational field intensity is equal 0. Okay, this is what shell theorem is. Is it clear, everyone? Sir, so keep in mind here, and in the afternoon session we discuss what is potential energy, what is potential. Okay, with this your gravitation gets over. Yeah, thank you all. Major part of gravitation over. Are you following, everyone? At least give reply.
Yes, sir.
Yeah. So we'll meet in the afternoon session, remaining things. Thank you all. Shall I end the session?